This mini lecture will cover a little bit more in depth about the crystal systems that we've already been studying. Again, a unit cell is the smallest repetitive volume which contains the complete lattice pattern of a crystal. So in one of these directions, this unit cell needs to be able to move, if you will, and you'll see the exact same thing, exactly this distance A back that way, or to the right this distance B, you'll see the exact same pattern from one step to the next. Now, based on these lattice parameters A, B, and C, and these angles alpha, beta, and gamma, we end up with 7 crystal systems, and those crystal systems have one or more lattices that can be or are developed from them. So these crystal systems, here's a really nice diagram of the crystal systems. This should be in your book. Again, this table is from Callister and Rethwich, 4th edition, and it's an excellent book. You should get it and keep it. Within these crystal lattices, we often find it necessary to identify locations and directions and planes. So we have developed a system where we can do this, and we can communicate these locations, directions, and planes. We're going to start off with locations and then move to directions. So in this cell, we have one side along the x-axis is A long, the side along the y-axis is B long, and the side along the z-axis is C long. So they could all be the same, A equals B equals C for a cube, or if it's some other parallelepiped, it could be that they're all different. And these angles aren't necessarily right angles here either. So this is a very general box-looking structure. So when we refer to a 1, 1, 1 coordinate, that simply means that if we start at 0, 0, 0 in one corner of this box, we move along the x direction, we move one lattice constant, which is the length A, one lattice constant in the y direction, which is B, and one lattice constant in the z direction, which is C. So it doesn't matter what A, B, and C are. We know that the 1, 1, 1 coordinate is at the far corner from our origin in this box. If you want to get to the center, we take half of that. So we go A over 2 to about this location here, B over 2 to about this location here, and C over 2 to about this location here. So when you want to go an integer multiple of lattice constants, or then if you go 2A, then you've gone 2 boxes over, or 2B is 2 boxes over, or we can even go in the negative direction along the y, z, or x-axes. When you get to those integer positions, that will be an identical position in the next unit cell. Here I have a model that I made up of a BCC cell. Now, the spheres aren't exactly touching. I've made them a little bit smaller. But you can see right here, let's assume that this is our 0, 0, 0. It's our origin. And this is coming straight out this direction. So this atom here, this is along the x-axis here. This atom here is along the 1, so it went out 1 in x, but it didn't go out anywhere in z, still along the same along the 0 part of z, and y is also 0 at this point. So this arrow going straight through this point matches, as its direction, matches the location. So this arrow here is along the 1, 0, 0 direction. Now this arrow here, to find its direction, we see that it's going through this atom. This atom is located 1a, or 1a along the x-axis, 1y, or 1b along the y-axis, but hasn't gone up any in the z-axis. So this would be the 1, 1, 0 location, and therefore the arrow here is along the 1, 1, 0 direction. Now for the final direction that we have here, this arrow is not just going through this atom, but it's also going through the center here, because I'm showing BCC. So this atom is at the 1A, 1B. Well, since it's cubic, A equals B equals C, so we can go 1 lattice parameter this way along the x, 1 lattice parameter along the y, and 1 lattice parameter along the z. That gets us to the location, the center of this atom. And since this arrow is going through from the center of this atom, which is at 0, 0, 0, to the center of this atom, which is 1, 1, 1, this arrow is in the 1, 1, 1 direction. To show you this a little bit better, so you can see it from different angles, I'll just move it slowly. And this is kind of the normal orientation that we see the ones in the book. So we have our origin kind of in the back there on the bottom. This arrow is coming out in the 1, 0, 0 direction. This arrow is coming out in the 1, 1, 0 direction. And this arrow comes out at 1, 1, 1. So you can see that from this perspective very easily. Okay, that was an easy one. Now we have to have a generalized way of doing these directions. So if we have a direction already, a vector, what we want to do is we want to reposition it first to make it pass through our origin. Now you can select an origin wherever you want to, but make sure that you select one of the corners of your box here. But it could be here, and then you need to use the box that's up here. So now we figure out what the projections are in terms of these unit cell dimensions. So if we have this blue one here, we try to read the unit cell dimensions A, B, and C. So along X, along Y, and along Z. So there's our spot that we're going to find. In fact, if you have another spot, as long as it's along that vector, that's okay, as long as you can easily read the directions, because all it is a direction. It doesn't have, it's not a length. So here, our location along that vector is 1 along the x direction, 0 along the y direction. There's no change in y, and it's only gone up like a half in the z direction right up here. So these are our first projections. We're only on step 2 here. Now we do not want to have any fractions in our directions or our planes. We can have them in our locations, but we want to make a common way of expressing our directions. So what we do is we make sure that we multiply through or divide through so that we have basically a simplified form of our projections that we read off to begin with. So we don't want any fractions, so we're going to multiply all of these through by 2, which is our common denominator here. So 1 times 2 is 2, 0 times 2 is 0, and 1/2 times 2 is 1. So that's part 3. Adjust to the smallest integer values. And then for directions, we enclose them in square brackets without our commas. So we repositioned the vector, we read off the projections, that's here, we adjusted the smallest integer values, and then we enclosed them in square brackets without commas. So this is the 2, 0, 1 direction. Now we have a new one. This one's actually going back into a cell that is behind our first cell. So we're going from this origin over to here. Could I adjust the origin to this location? Yep, I could, but then this would have to be 0, 0, 0. So let's just stick with this being 0, 0, 0. So we go back in x by 1, so it's -1 there. We go forward in y right here, so that's a +1 in y, and then we go +1 in z. Well, we don't have any problems with integers, it's just 1, so we don't have to multiply or divide through. And then we put it into the brackets, and instead of putting a -1 here, we put a 1 with an overbar. So we call that the 1 bar 1 1 direction. If we have something else, for example, we found the 2 bar 2 2 direction, that would actually be part of the same family of directions as the 1 bar 1 1. It would be essentially the same direction as 1 bar 1 1. If instead we found something different, for example the 1 1 1, and it was in a cubic plane or a cubic system, then that's pretty much the same thing. You can't really tell if you rotate at 90 degrees which direction it was, whether it's 1 bar 1 1 or 1 1 1. That indicates a family of directions. We'll talk about that in a sec. Just wanted to show you something on the screen here. If I took this one, this 2 0 1 direction, and instead of that spot I wanted to come out to this spot. Okay, here we have, it's the same direction. Just wanted to show you what we can do with that. And forgive me for a second for having a hard time drawing this, but come all the way out to here and out to here. That's a little better. And let's consider that this comes to this direction in that spot. What we end up with is hopefully the same thing. Instead of going out 1 in x, 0 in y, and 1/2 in z, we come out 2 in x, and we still haven't gone anywhere in y, we're still in this plane here, and we go up 1 in z. So we end up with, for this step, 2 0 1, which is in fact what we have already. The difference is that we don't have to worry about step 3, adjusting to smallest integer values, because we're already there. That just indicates that what we have for the direction here is the same no matter how far we go. Again, it's just a direction, not a length. Okay, to better illustrate our crystallographic directions, I have a nice program here from the wonderful folks at J. Wiley. Again, by the Callister and Rethwich textbook. I use the integrated material science textbook, and it's very, very good. What we're looking at here is the 1 0 1 bar direction. So I come out 1 in x, not going anywhere in the y direction, so I'm not coming out this way at all, and I'm going 1 down in z. So this 1 0 1 bar direction. here, I have the one bar one direction. So come out 1, go back in y, go negative in y 1, and then I go up 1 in z. So this becomes the one bar one direction. This one should be fairly familiar. We just did this one. This is the 2, 0, 1. So it sometimes is a little tough to work with because you don't see it going 2 in x. You only see it going 1 in x. You understand the y because it doesn't go anywhere in y. And it's only going a half in z, but it indicates 1. Well, again, that's because this is going to go, if it keeps going, all the way up to this point, somewhere up there, and that will be 2 in x, 1 in the z direction, and again, we haven't gone anywhere out of the plane, so the y direction is still 0. So here we have the 1 bar 2 1 direction. 1 bar 2 1. What does that mean? That means we're going to go back here 1 in the x, and then we're going to go 2 positive in the y direction all the way out here, and then we're going to go up 1 in z. And you could rightly say that no, that's not where this ends up right here. Again, that is its distance, but it does have the right direction, and if you keep traveling, it will go out to that location eventually, and it will continue on. Again, what we're looking for is the overall direction, and to be able to make sure that we're talking about the same direction, whether we're talking about going from here to here, or from here to way out here, or for that matter going from this location all the way out this direction. These two are part of the same family, basically the same direction. You could even talk about taking this one and kind of bring it all the way up into the screen here, or bringing this one out like this. It might be part of the same family of directions. Next is the 1 bar 2 3. So this can get, again, somewhat confusing, but it's the same principle. If I look at this from just this particular arrow and its length, I am coming out only about 1/3 in x. And then I'm coming over about 2/3 in y, and then I'm going up a full 1 in z to about that point. So if I'm going over negative 1/3 in x, about 2/3 in y, and going up a full lattice parameter in z, I take these and I multiply through by the common denominator, 3, so I end up with -1. Multiply this through by 3 and I get 2. Multiply this through by 3 and I get 3. Then I put it in brackets, remove the commas, and use an overbar for the negative sign. And of course that's a 1 bar, 2, 3. Notice for any of these we didn't actually have any directions or units here. So in fact this could be a cell that has maybe this is 90 degrees, maybe it's not 90 degrees, but it has a cell here where this length could be a nanometer, it could be half a nanometer, and same thing with this. This could be 8/10 of a nanometer, this could be any length. The point here is to have a common way of describing these various angles so that we can communicate better and compare different materials and their directions better.